My name is Kristina Gligorić. I will talk about our work, Bytes, on the validity of estimating food consumption from digital traces. This is joint work with Irena Đorđević from University of Niš and Robert West from EPFL. To be able to improve diets, researchers and stakeholders need to know what foods people consume. However, monitoring diets at the population scale is challenging. There is great promise in using passively collected digital data to estimate food consumption. These digital datasets are unmatched in terms of scale. They are big, they're always on by default, and they're often non-reactive or passively collecting, among other benefits over traditional methods. And given this potential, researchers have been developing and applying their expertise to studying diets via passively collected digital data. However, digital traces are not primarily collected with scientific studies in mind. Found data may introduce new biases that threaten validity in their own ways. For instance, measurements can be error-prone. The traces are not representative and they're often drifting in time. So despite their potential, error-prone and unreliable data and methods may do more harm than good if handled without the required caution. Methods that offer insights into the validity of new measures become increasingly necessary, and it is in general unclear how do we think about the balance between the advantages and drawbacks in a rigorous way. To illustrate, food is very prevalent in art and important for culture. As scientists, we study such traces that we leave behind as part of our modern lives. However, for example, studying paintings, one could not blindly assume that paintings accurately reflect people's behaviors at the time. It is known that paintings prominently featured the foods that were aspirational to the commissioners, aesthetically pleasing, and overall we know that food art does not reflect reality. I will describe how we develop a bias estimation framework and perform a case study of food consumption in Switzerland. Since the goal is to investigate the validity of studying diets with digital traces, we focus on the case study of Twitter. We collected food images posted on Twitter from Switzerland between 2017 and 2020, following data collection methods from the literature and aiming for completeness by using full archive search endpoint. We also performed automated and manual annotation of the collected images, which overall resulted in 3,700 images of food. Then, in order to establish a link between online and offline dietary behaviors, these images are contrasted with food that people tracked via a food tracking application. And the food present in these images was actually consumed, since the purpose of the application is to track users' personal food consumption. Images in both datasets are mapped on the food type level, time period, and they're both collected in Switzerland. And then our overall research question asks, is social media a bias or a truthful mirror of actual food consumption as measured by food tracking? The two sub-questions are particularly important. The one about biases of food type distribution. To what extent do food images posted on Twitter reflect the types of actually consumed food as measured by food tracking? And the second one about biases within the food types. For a given food type, to what extent do images posted on Twitter reflect the nutritional properties of actually consumed and tracked food of that type? Having described the data, we are already able to answer the first question regarding bias of food type distribution. We compare the prevalence of the 155 food types across the two sets. So on x-axis, we have frequency of the food type among Twitter food, and on the y-axis, the type frequency among consumed and tracked food. So if a food type is on the diagonal, it means equally common among the two datasets. First, we can observe a significant positive correlation. The more frequent a food type is among consumed and tracked foods, the more frequent it tends to be among the tweeted foods. That said, although food type frequencies are correlated, important deviations can be observed. For instance, bread and butter are underrepresented on Twitter, while on the other hand, foods such as cake, soup, chocolate, raclette, burgers are overrepresented on Twitter. Now, having established biases of food type distributions, we develop a bias estimation framework relying on pairwise comparisons of images with foods of the same type. Since judging between two alternatives is generally easier and more intuitive for humans than assigning a score, we adopt a pairwise paradigm where we confront human raters with pairwise choices and then later infer latent scores from such pairwise preferences. For example, images A and B both feature a pizza, And then since previous work notably used social media to estimate nutritional properties, appearance, and perception, we operationalize 4 dimensions along which we contrast tweeted and consumed food. We collect pairwise preferences by asking participants which image contains pizza that appears more tasty, more healthy, more caloric, or more likely to have been consumed at home. In total, we collect 12,000 such pairwise comparisons for each of the 4 dimensions. For the 2 example images, A and B, we observe human preferences, where preference is a random variable, and then the target quantities, scores of images A and B, with respect to how tasty the food is, can be inferred from the observed preferences following a Bradley-Terry model, where we assume that each image has a latent tastiness score, and the probability that a rater will prefer image A over image B in a pairwise comparison is proportional to its score. And then given this setup, maximum likelihood estimation is used in order to infer the latent scores that best explain observed preferences. Then, although only pairwise choices are made, we can rank all images based on their latent scores. So for example, on the x-axis, we have the estimated tastiness score, on top the distribution of Twitter food in blue, and in bottom the distribution of logged food in orange. We can see on the first glance that they are shifted and that Twitter pizzas tend to have higher scores. In the example, image A is actually estimated to be the tastiest among pizzas on Twitter, whereas B is the median among the tracked pizzas. It is very informative to take a median image among Twitter foods and check its estimated latent tastiness score, and then see how the median Twitter pizza would rank among consumed pizzas. So in case of tastiness, a typical median Twitter pizza would be among the tastiest 14% of logged pizzas. And then overall, comparing the ranks, we find that food posted on Twitter compared to consumed and tracked food is perceived as significantly more caloric, more tasty, but less healthy and less likely to have been consumed at home. It is very informative to try to better understand why the crowdsourced participants perceive the food as such by analyzing the free-form tags that were provided as justification. So for instance, top tags typical for my repo food are plain, bland, simple, boring, whereas top tags typical for Twitter food are fancy, fresh, colorful, delicious. Overall, the prominent themes in tags that are discriminative of consumed compared to tweeted food are related to complexity, portion size, ways of preparing, and presentation. So to summarize, the food shared on social media and actually consumed and tracked food significantly diverge from each other. However, we cannot assume that the food consumption measured with food logging perfectly reflects the true food consumption in the general population, due to, for instance, selection biases in who uses food tracking and how. So strictly speaking, the true food consumption in the general population remains unknown. In particular, if we focus on the average tastiness, tweeted food is perceived as more tasty than the consumed one, and the true food consumption might be somewhere in between, with either food tracking or Twitter being a less biased proxy. It could also be that the true food consumption is even less tasty than as captured by tracking, or even more tasty than captured by Twitter. However, either way, at least one of the two, the tracked food or the one on social media, differs from the general population by at least half of the measured bias, and therefore is not a faithful representation of the actual food consumption in the general population. So to summarize, this work contributes a novel crowdsourcing framework for estimating biases and a case study of estimating food consumption in Switzerland with social media and food tracking. We find that overall, food shared on social media and actually consumed and tracked food diverge from each other. This divergence implies that at least one of the two proxies is not a faithful representation of the actual food consumption in the general population, and therefore we establish a lower bound on the bias between the two proxies and the general population. Thank you so much for your attention, and for more details, please check out the full paper.